All right, so we are starting 12.2, which is finding limits algebraically. So the first thing we need to do is we need to talk about all of our different limit laws. So in order to use these limit laws, there's some requirements. The first requirement is going to be that we know that C is a constant and that the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist. Notice on both of them, x is approaching the same value. It's just the function names are different. So we have these 7 limit laws to begin with. Limit law 1 says the limit of a sum is the sum of its limits. So if I'm asking for the limit as x approaches a of f of x plus g of x, I could take that and say, well, that's the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So if I have the sum of 2, I could split it into 2 different limits. The same goes with the difference. Okay, so that's limit law 2. For the third one, it says the limit of a constant times a function is the constant times the limit of the function. So what that's saying is if I'm asking you for the limit as x approaches a of c of f of x, I could pull that c out front and then find the limit as x approaches a of f of x. So you take c times whatever value that comes out to. Then number 4, we have the limit of a product is the product of its limits. So the limit as x approaches a of f of x times g of x is equivalent to the limit as x approaches a of f of x times the limit as x approaches a of g of x. Okay, the same is going to go for the quotient. The limit of a quotient is a quotient of its limits. However, we have to have a little bit of a restriction there. So when we look at this, we're going to say the limit as x approaches a of f of x divided by g of x is equivalent to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, as long as the limit as x approaches a of g of x is not 0, because I can't divide by 0. Then we have the limit law that says the limit of a power is the power of the limit. So if I say the limit as x approaches a of f of x raised to the n power, I could find the limit as x approaches a of f of x and then take that value and raise it to the nth power, where n is a positive integer. And then the last one is the limit of the root is the root of the limit, which is saying that if I take the limit as x approaches a of the nth root of f of x, I could say that's equivalent to taking the nth root of whatever that limit is. So the nth root of the limit as x approaches a of f of x, where n is a positive integer. And if n is even, we assume that this limit is greater than 0. So that we're taking the limit of a positive. When we take the limit, we get a positive number out so that we can actually take the radical of it. All right, so let's take a look at this. I'll zoom out for a second so we could see. So this graph here, we will call this piece is f of x. So the darker piece is f of x, and the lighter piece is the graph of g of x. So here and there. Okay, so it says, find the limit as x approaches -1 of the sum of f of x plus 5 g of x. Now, we can't just write an answer. What we have to do is we have to evaluate it using the limit laws. So we're going to evaluate it using the limit laws, and then we're going to justify each step. So I'm going to say something like, well, this is the sum of limits. So I could say this becomes the limit as x approaches -1 of f of x plus the limit as x approaches -1 of g, 5g of x. Okay, so this statement is equivalent to that statement. And then now that I have this, right here, I could use another limit law. That limit law is going to be the one that says the limit of a constant times a function is the constant times the limit of the function. So this is going to be equivalent to the limit as x approaches -1 of f of x plus 5, the limit as x approaches -1 of g of x. And now we can evaluate that and say what it is. So here, the limit as x approaches -1 of f of x. So we're looking here. So what happens right here? And then what happens right here? So if this is 1, 2, 3, 4. So at -1, I'm at 4. So the limit as x approaches -1 of f of x is going to be 4. Oops, that pen doesn't work. Let's try another one. Plus 5 times on g of x. So as I approach -1 from the left, or if I approach it from the right, so there's -1, let's call that -2. So we'll call that -2. So the limit as x approaches -1 of f of x plus 5g of x is going to equal 4 plus 5 times -2. So 4 plus -10. So it's -6. All right. So when we look at B, we have the limit as x approaches 1 of f of x times g of x. Well, there we can use that the limit of a product is the product of the limits. So I could take that and I could rewrite it as the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. Now I could look at my graph and I could say, okay, when x approaches 1 of f of x, five, we'll call that 5. And the limit as x approaches 1 of g of x, I'm going to call that -2.5. Okay. And then when I multiply those together, we get -12.5. On C, we're looking for the limit as x approaches 2 of f of x divided by g of x. On that one, we could use limit law number 5 that says the limit of the quotient is the quotient of a limit. So the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x. Okay, so on this one, we have to make sure that this piece exists and isn't 0. So the limit as g of x approaches 2. Well, it's fighting. So this limit doesn't exist here. So can I take something divided by that doesn't exist? Well, that's still going to be does not exist. I actually cannot tell you what the quotient of those two would be. On D, we're looking at the limit as x approaches 1 of f of x cubed. Okay, so that one is saying limit law number 6, the limit of a power is the power of the limits. So I could say this is equivalent, make sure we're using our equal signs, equivalent to the limit as x approaches 1 of f of x, and then I'm cubing that whole piece. So the limit as x approaches 1 of f of x we said was 5. So this piece here is 5, and then I'm cubing it. So 5 cubed is 125. We do have 4 other special limits. This one says the limit as x approaches a of any constant is equivalent to that constant. So the limit as x approaches 5 of -7 would be -7. Here we have the limit as x approaches a of x is going to be a. So if your function is just x, then as x approaches a, the limit as x approaches a of x would be a. Here, the limit as x approaches a of x to the n is going to be a to the n, where n is a positive integer. So again, if your function is just x and then raised to a power, then whatever you're approaching is going to be raised to that same power. And then for number 11, it says the limit as x approaches a of the nth root of x is equivalent to the nth root of a, again, where n is a positive integer and a is greater than 0, because I can't take the square root of a negative number and get a real output. Okay, so using limit laws, evaluate the following limits and justify each step. So you just can't give me an output. You can't just tell me what the limit as x approaches 5 of this function is. You need to show me each step. I'm going to ask you to pause your video and try A and B on your own. And then when you've had enough time, go ahead and press play again. Okay, so when you look at this one, we're going to split it up into many steps. You can't just have one step. You can't just say equals 39. Okay, if it is asking you to use your limit laws and justify each step, you have to have multiple steps. So your first step is going to say, well, this is equivalent, so an equal sign, very important, to the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. We're able to do that because of the addition and subtraction limit laws. Then on your next step, you could pull that 2 and that 3 out front because they're constants in front of a function. So you could say 2 times the limit as x approaches 5 of x squared minus 3 times the limit as x approaches 5 of x plus the limit as x approaches 5 of 4. We're able to do that because of the constant limit law. And then I could take that power and bump it up front and say and bump it out. Take that power and bump it outside. So 2 times the limit as x approaches 5 of x, all of that squared, minus 3 times the limit as x approaches 5 of x plus the limit as x approaches 5 of 4. And that's the power limit law. And then we're left with these three, which are all special limit laws. Okay, so the limit as x approaches 5 of x is a special limit law that just tells me it's 5. Again, the limit as x approaches 5 of x, special limit law. And then here, the limit as x approaches 5 of 4 is 4, special limit law. And then that limit is equivalent to 39. All right, looking at part B, we're going to start off with our quotient limit law. So we're going to split it up into say the limit as x approaches -2 of x cubed plus 2x squared minus 1 divided by the limit as x approaches -2 of 5. Oops, I copied it down wrong. 5 minus 3x. And then we could use our addition and subtraction limit laws to say that's going to become the limit as x approaches -2 of x cubed plus the limit as x approaches -2 of 2x squared minus the limit as x approaches -2 of 1 divided by the limit as x approaches -2 of 5 minus the limit as x approaches -2 of 3x. Again, those are addition and subtraction limit laws. Then I could use my constant and power limit laws to say the limit as x approaches -2 of x cubed plus 2, the limit as x approaches -2 of x, that quantity squared, minus the limit as x approaches -2 of 1, divided by, and this says the limit as x approaches -2 of 5 minus 3 times the limit as x approaches -2 of x. And then now when I look at this piece and this piece and this piece and this piece and this piece, I see they're all my special limit laws. Okay, they're all special limit laws. So using my special limits, I could say -2 cubed plus 2 times -2 squared minus 1, all of that divided by 5 minus 3 times -2, which gives me -1/11. Okay, but if you would have just put -1/11 when it asks you to justify each step, you wouldn't be able to get full credit. So be careful and make sure you're reading instructions. Now, the last thing we're going to talk about is limits by direct substitution. You need to have the requirements met. The requirements to use direct substitution says f is a polynomial or a rational function, and a is in the domain of f. So the limit is the value of f of a if the limit as x approaches f of a, or sorry, the limit is the value of f of a is what direct substitution tells us. That's telling me that the limit as x approaches a of f of x is equivalent to f of a. So let's see how that works. Using direct substitution, it says evaluate the following limits. The limit as x approaches 3 of 2x cubed minus 10x minus 8. So this is a polynomial. And 3 is in the domain because the domain of this polynomial is all reals. So because that is true, I can do direct substitution and say that this is equivalent to 2 times 3 cubed minus 10 times 3 minus 8 by direct substitution. And so when we do that, we get 16. So the limit as x approaches 3 of this function is equivalent to 16. And we could do that because of direct substitution. Now let's look at b. b is a little different because I have a rational function. So I know the domain of the numerator is all reals. The domain of the denominator is all reals, but remember your denominator also can't equal 0. So let's make sure if I plugged in -1, I wouldn't get 0. -1 to the 4th is 1, plus 2 is 3, so we're okay. -1 is in the domain of the function. So then I could do direct substitution, and this is going to be -1 squared plus 5 times -1, all divided by -1 to the 4th plus 2, which gives me -4/3. Okay, so you only could use direct substitution if this value is in the domain of this given function. Sometimes you have to use a little manipulation to use direct substitution. So for example, on this one, when I look at it, it says the limit as x approaches 1 of x minus 1 over x squared minus 1. Well, notice if I plug 1 in, 1 squared minus 1 is going to give me 0. So right now, a is not in the domain. But what we can think about is we can look at this and say, well, this really is the limit as x approaches 1 of x minus 1 over this factors x minus 1, x plus 1, which makes those two cancel. So this is equivalent to saying the limit as x approaches 1 of 1 over x plus 1, since those two cancel. And then 1 is in my domain here, so I could do direct substitution and get 1/2. You cannot go from here to here, because if I left it like this and these weren't crossed out, you're going to have 0 divided by 0 times 2. Algebraically, I can't do that. So you have to show this step, then you could evaluate. When we look at this one, what we notice is, again, a is not in the domain of this function, because if I plug in 0 there, I'm going to divide by 0. But let's see. What happens if I simplify this numerator? So what happens if I look at this and I say, well, this is equivalent to saying the limit as h approaches 0 of, this is 9 plus 6h plus h squared minus 9 over h. Then what you notice is, oh, those two 9s can simplify, and those two both have an h in it. So that gives me the limit as h approaches 0 of h times 6 plus h over h, which can simplify to the limit as h approaches 0 of 6 plus h. Now I could do direct substitution and get 6. Okay, so recall that you can't just go straight from step 1 to the last step. You have to show this first step, this second step, this third step. I can't take the limit right here. Okay, it's not able to do, but once I cross out those h's and show that I'm taking the limit as h approaches 0 of 6 plus h, then I could do direct substitution. Okay. The last one, which is a trickier one that we don't always think about, is when you rationalize the numerator. Okay. So right here, when I look at it, the limit as t approaches 0. Notice I can't do direct substitution because 0 squared is 0. I can't have 0 in my denominator. So what we're going to do is we are going to try to, since I have this weird square root, I'm going to say, well, what happens if I try to rationalize my numerator? So that would give me, to rationalize it, I'm going to multiply it by the conjugate. So that's going to be the square root of t squared plus 9. And then the conjugate here would be plus 3. So notice that the first term stays the same. I'm switching this operation, opposite operation. The last term stays the same. If I multiply the top by that, have to do the same to the bottom. Okay, so that's going to give me the limit as t approaches 0 of my top. Let's get this times this will give me t squared. Notice my middle terms cancel out. So t squared minus 9 sorry, I missed a piece here. This times this is going to be t squared plus 9. Okay, so this whole thing, t squared plus 9, and then minus 9 over, and then just don't distribute that in. It's just t squared, the square root of t squared plus 9 plus 3, which is going to give me the limit as t approaches 0 of t squared over t squared times t squared plus 9, the square root of that, plus 3. And now notice here t squares cancel out. So you get the limit as t approaches 0 of 1 over the square root of t squared plus 9 plus 3. And now all of a sudden, in this piece, 0 is in my domain. So I could use direct substitution, and I get 1 over, if I plug 0 in there, 9 square root of 9 is 3 plus 3, 6. All right. So kind of what we're seeing is sometimes you can manipulate the problem a little bit in order to use direct substitution. Okay. So that is our lesson for finding limits algebraically. For homework, I believe we're going to do 12.2, 1, 3, 4, 9 through 11, 27, and 32.